This is part 3 of our final exam review for statics. In this part of the review, we're just going to cover chapter 6, which was trusses and frames and machines. So the overarching guidance I have here for the vast majority of these problems is first, draw a whole free body diagram, a full, complete free body diagram to solve for the reaction forces. Very few cases where you aren't going to need that whole free body diagram. Then, once you have those reaction forces, break it apart to find internal forces. And when you're doing that, especially with trusses, don't forget to include those reaction forces that you solve for. We'll look at a couple of examples in just a minute. When solving trusses, we have two different approaches that we can use. One is to take joints and draw diagrams of individual joints. So an example of a joint diagram might look like this. We've got a joint, it's got an externally applied 2 kilonewton force, and it might have 3 different members all connected. I like to draw all of my forces as pointing away from the joint. What that means is that the member sitting over here, in this case member AD, is pulling to the right. It's physically to the right of joint A, and it's pulling to the right on joint A. This arrow means that member AB is physically sitting to the left of joint A in a horizontal position, and it is pulling to the left on joint A. And this arrow indicates that there is another member at an angle down and to the left that is pulling down and to the left. So when you draw the arrows out and away like this, it means you're assuming that the member is in tension. So if you get a positive sign when you actually go and solve for these, that means that member was actually in tension and you were correct. If you get a negative, it means that they were in compression. We also have another strategy we can use with trusses, which is called taking a section. And when you take a section, you're typically going to keep a large amount of the truss connected, and you're only cutting open to be able to find potentially 3. So you only want to cut through 3 members, and that will enable you to find the forces in those 3 members. Okay, what are the pros and cons? Joints are simple. And if you need to find the force in every member of a truss, you should use method of joints. It is simple because we can only sum forces in the X and the Y direction. We wouldn't be summing any moments. So this is good when you need to solve for every member. Sections are slightly more complicated. With sections, you need to make sure that you only cut open 3 members, exactly 3 members. And the reason for that is we're going to use 3 equations. We're going to sum forces in the X, sum forces in the Y, and sum moments about a point. And we're going to set all of those equal to 0. So we can solve for 3 unknowns. You only want to cut open 3 members, so you have exactly 3 unknowns. So a little more complicated because you do have to cut it open. You have to be careful to make sure that on whichever side of the cut you decide to keep, in this case it's over here, that you include any reaction forces and any applied forces. But anything that happens on this mysterious other half of the truss, we throw it away. We don't use it at all in this part of the calculation. So it's crucial with sections that you first find the reaction forces before you start cutting it open, because now we've discarded the other half of the truss, and without it, we would never be able to find these reaction forces. We do have to sum moments. It is usually helpful to sum moments at a point like, oh, this location right here, so that 2 of your unknowns disappear and you can solve for the 3rd one right away. And then you could also maybe sum moments about this point right here where these 2 forces meet. And then you'd be able to solve for this one. And then finally, summing forces in the X or Y direction will give you the 3rd unknown. So section cuts are good when you only need a few of the member forces. If you need all of them, I would use joints. I don't see any value to using sections if you need to solve for every unknown. Let's look a little bit about cutting sections. I've put a couple of trusses in here that I think you've seen in your homework before, but if I needed to find the force in member HI, HC, and CD, well, you're going to do a cut, like I've shown with that blue dashed line, straight down through those 3. And you can keep either the left side or the right side when you draw your free body diagram. This happens to be a truss that you could take a shortcut and not find the reaction forces when you begin, but that's only because the reactions are all over here on the far left. We're taking a cut down the middle, And so we can actually solve for these using a free body diagram that only keeps the right part of the truss, which has no external supports and no reaction forces on it. So my section diagram, it would look like this. I like to actually include the little cut off, right? I'm cutting right here. So I want to include this little part of HI, this little part of HC, and this little part of CD to remember that they were there and what direction they act. And then out here, I would have a 1,500-pound force at point F, 1,500-pound force at point E, and a 1,500-pound force at point D. And then I would put on my three unknown forces, the force in HI, the force in CH, and the force in CD. And to solve for these, let's just do one of them. We could go ahead and take some moments about, say, point H right here. And so if I go to some moments about point H, those have to add up to 0. We'll assume counterclockwise is positive. So FHI and FCH cause no moment because they go right through that point. But FCD will cause a clockwise moment. So I'm going to call that minus FCD. Its perpendicular distance is right here. The force is in the horizontal direction, so the perpendicular distance is the 4 feet down to it. So FCD times 4 feet. And then the other three forces, let's see which will cause moments. This 1,500 right here is actually lined perfectly up with point H and will not cause a moment. This one, however, is 3 feet away, and it will cause, since you have from point H, you go right 3 feet and down, it's going to cause also a clockwise moment. So I'm also going to call that minus 1,500 pounds. It's 3 feet away. And finally, the other 1,500 pounds will also cause a clockwise moment about point H, and it's 6 feet away. And that all equals 0. And it comes out to be minus 2,250 pounds. What does the minus mean? Well, I drew it assuming it was in tension. Well, it's because I drew the arrow as starting at the joint and going out and away. That means I assume this member sitting to the left of point D is pulling on point D. That means point D would be pulling back to the right on the member. So that means tension. Then I got a negative sign. So what that means is that FCD is actually 2,250 pounds in compression. Well, how would I then use that? I prefer to leave my free body diagram alone and simply remember going forward that FCD, when I plug it into any other equations going forward, I need to remember the negative sign. Let's look at the second one. The second one is a truss where you absolutely have to find the reaction forces first. So first, we're going to draw a whole free body diagram. That will look something like this. We've got a bunch of downward forces acting on it. And then at E, we have a roller, so we'll have just an EY. And at A, we have a pin, so we'll have both an AY and an AX. So it's a great two-dimensional diagram. We need to solve for all three of those unknowns. We'll do that using our equilibrium equations. And we're going to sum forces in the X, some forces in the Y, and some moments, probably about point A or point E, either one will work, and solve for those unknowns. Solve for AY, AX, and EY. Now, this problem asks for what's happening in CD, CF, and FG. So the logical cut to do that would be straight down in between the three. You could keep either everything to the right or everything to the left. I like to keep the smaller side. So the smaller side for my section would look like this. I have a little triangle. I have my external loads, my 3 kilonewtons, my 5 kilonewtons. I have my unknowns, the force in CD, the force in CF, and the force in FG. And I have EY. Very common mistake I see with trusses is forgetting to put the reaction forces on the free body diagrams. What if we needed to use a joint diagram for some reason here? So an example might be maybe the problem asks for these three, so use a section cut. And then what if it randomly also asks you for the force in DF and the force in DE? once you've solved for the force in CD, joint D is actually a very easy way to get those other two. You don't need to do another section cut. So fourth, we could do joint D. And what would that look like? Well, joint D is sitting right here, and it's got 5 kilonewtons downward, an unknown force in DF pointing downward. I'm assuming it points downward, and I'm wrong, but I always draw all my unknown forces as tensile forces. There's my force in DE, and there's my force in CD. So from my section diagram, I would have solved already for the force in CD. So now on this diagram, I only have 2 unknowns. If you sum forces in the y direction, you'll find that the force in DF will be equal to actually negative 5 kilonewtons. So DF will be 5 kilonewtons in compression. And the force in CD, whatever it came out to be, force in DE will have to be exactly the same. I have seen a lot of mistakes with tension and compression. Basic idea is that when you draw a diagram of a section or a joint, you're drawing the force that that member applies to the thing on your diagram, which means if I have a joint and the force is going outward, this is the force the member applies to the joint. It does not mean that the joint is pushing to the right on the member. It means the member is pulling to the right on the joint. So if I were to then draw the member itself, I need the force, the interaction between the joint and the member need to be an equal and opposite pair. So I would need to then draw this force here and this force there. So whatever the force is, if this is the force in AB, this is the force in AB, and this is the force in AB, and then maybe if that's joint A, here's joint B over here, you end up with another equal and opposite pair. There's the force in AB as well. So this is what tension looks like. The joints A and B are pulling outward on the member, so the member is in tension. When you see that on a joint diagram or a section diagram, tension looks like this. So frames and machines are the other part of this chapter, and the thing to remember about frames and machines is if you have even one member that is not a two-force member, then it's suddenly a frame or a machine. And it looks like all of my diagrams I've included in here are actually machines and not frames. What could a frame look like? Well, often a classic frame we have sometimes looks like this. A horizontal member, a vertical member, another vertical member, and then what if we add another member across here at a diagonal, and then maybe we clamp one of these. There's a few different ways to end up with something that's not just a truss. So because this vertical member right here is continuous, it's not a two-force member because it has something meeting in the middle and applying a force to the middle of it. Two-force members can only have forces at their endpoints. It's also not a truss because it has a clamp over here, and trusses can only have pins and rollers because this clamp would create a reaction moment, which all by itself means that this would not be a two-force member. But frames and machines can have some two-force members in them. In this case, this top member might be a two-force member, and this slanted one, the sloped one, might also be a two-force member. So we'll use that in our solution to try to make things a little bit simpler. The idea behind frames and machines, though, regardless, is if it is a frame so that it's actually fixed to the ground somewhere, you do want to start with a whole free body diagram. If it's a machine, you oftentimes can skip that and just go straight to plucking things apart. But at some point with these, you are going to need to draw separate free body diagrams. So I had a couple of rules to remind you about with drawing frames and machines. Rule number 1, same point on the same part, forces in the same direction. Rule number 2, if it is the same point on a different part, forces must be equal and opposite. So let's have a really quick look. These pliers I think should look familiar. You may have seen them on a recent homework or exam. We can draw a diagram of that member that I just colored in right there. So that member, EDC, at point E, there would be a force at E just in the y direction because we're pushing straight down on that little twig, and so it's pushing straight back up. At point D, it's just a generic pin, and the thing it's attached to is not a two-force member, so you need to draw both a dx and a dy. And then finally, point C is attached to a two-force member, so we always want to be on the lookout for our two-force members. So at point C, Instead of drawing two unknown forces, I need to draw a single force that I'll call the force in member BC. And that should be a whole free body diagram for that member. Let's look at some other parts that we could draw free body diagrams of. We could do this top piece right here, which has a handle, goes down around. So this one is pinned to the other things at point D and point A. So let me draw this purple shape. Down, up, over, something like that. Not the best drawing. So what it has acting on it is a force P. At D, remember we already drew D on a different part. So at point D on this part, we need the forces to be opposite of what we already drew. So we got to go left for dx and down for dy. And then this also contacts something else at point A. So at point A, we'll do an AX and an AY. And that looks okay for that diagram. That's all. The only places where it contacts anything are at A, D, and P. The reason at A we have an AX and an AY is that the thing it is pinned to at A is really complicated. It's not just a two-force member. So let me draw that one. Maybe make it my orange part. Looks something like that. See if I can draw it. On this part, we also have the force P. At B, we got the other side of our two-force member. So if I drew this one going down and to the left, this has to go up and to the right. And at point A, I already drew A on something else. So I better draw the AX and AY in the other direction compared to where I drew them on my other diagram. And then here's the other EY. And these two also need to be an equal and opposite pair. And what I've got now are a set of diagrams that look a little bit complicated because if you'll notice, every single diagram has four unknowns on it. So this is not going to be a very fast problem to solve. I usually like to try to find the diagram with the fewest unknowns. In this problem, you're either going to be told what EY is or what P is. Now, if I'm told that EY, say the cutting force is 20 pounds, then the diagram I'm going to start with is this guy right here. Because if I know EY, then I've got actually exactly three unknowns on this diagram. So I can solve for all three of them. I could, for example, sum moments about point D. That would give me FBC. And then I can sum forces in the X. dx will equal this component of FBC. And dy and EY have to add up to this component of FBC. Then I'd probably, since I found all the forces at D, I'd likely move on to this purple diagram. Point D and A are right above each other. I already know the forces at D. I want to find P probably. So I'm going to sum moments at point A. And since D is right above it, dy will not cause a moment. I'll simply have dx times this distance, causing a moment in one direction, and P times this distance, causing a moment in the other direction. And that would be my strategy to solve this problem. This next one is very similar. It's also a kind of a cutting tool. You want to notice that there is a two-force member in ED. And this one is symmetric. It actually has, a jaw on the bottom and a handle on the bottom and a jaw on the top and a handle on the top. So you probably only need to draw two of those to solve the problem. So I decided to just draw the top ones. So let's start with this little jaw. Looks kind of like that. It's going to have a force at C. ED is a two-force member, so I'm going to have the force in ED straight up and down. And then at point A, I'm going to have some kind of an unknown AX and an AY. And that's actually, even before you've drawn any of their diagrams, you can see that's going to be a great diagram to start with, because what happens if you try to sum forces in the X? You can instantly tell that AX is equal to 0. And second, I'd probably draw this diagram of the handle part with the grip. Looks like it comes over and then down like that, maybe. So we're told that this one has 100 newtons on it. And then at A, we would need our AX to go the opposite direction and our AY to go the opposite direction as what they did in the other diagram. And then I would need FX and FY. Well, we already found out that AX is equal to 0. So this is a great diagram. It actually only has three unknowns on it. And I'm thinking I want to sum moments about point F. Because if I sum moments about point F, first it's pretty quick because I've only got the 100 Newton force that I know and AY that I don't know. And if I can sum that moment, I'll solve for AY. Then I can come back to this diagram. And since I know AY, I can sum moments about this point right here, point E, and I'll be able to get CY really quickly from that diagram. Summing moments about F is a little tricky with this problem because of the angle, but it's not too bad. All we need to do is do a little bit of work on getting perpendicular distances. So from point F, you can see that the distance along this handle is 400 millimeters. So what I would actually like to do is maybe split my 100 Newton force into a arrow that's perpendicular, a force component that's perpendicular, and one that's parallel. The one that's perpendicular would be 100 cosine 15, and it's 400 millimeters away from point F. The one that's parallel would be 100 sine 15, and it looks like it's 20 millimeters away from point F in a perpendicular sense. And then for point A, again, I want that vertical force AY, I want its component. I want to find out how much of a moment that causes about point F. So I'm going to take that AY, split it into a component using AY cosine 15 that's perpendicular to the handle. Well, that's directed right at point F and causes no moment. And then I'll have a little force component at A that's parallel to the handle that's exactly 20 millimeters away. So you multiply just that component of AY that's in the direction of the handle times 20 millimeters. That would let us solve for AY. And then we could go back to our original diagram and solve for CY. This backhoe, similar idea. This one is to remind you that when we have hydraulic cylinders are always two force members. So to solve this one, I like to think about breaking things apart. So you got like maybe 2 or 3 joints in them. So let's try that blue part of the bucket. It would have a weight acting downward on it. And at H, it's connected to something complicated. That just means that I'll have to draw both an HX and an HY because it's not connected to a 2-force member. But now up at point F, we are connected to a 2-force member, so that becomes an FEF. And that's a great diagram. It only has 3 unknowns. So I would most likely sum moments about point H, but the weight here times that distance. And then FEF, I would need to find a perpendicular distance. Oh, I have a 30-degree angle. That's what I have. So with a 30-degree angle, I'll be able to figure out a perpendicular distance to point H. Then I would also need a diagram of another part. So when I solved this, I actually did this member CDH. So CDH is not exactly horizontal, but at C, there's something complicated going on. So we need to draw both CX and CY. At E, that's the other side of that 2-force member. So here we go with FEF again. And then at H is the other side of this HX and HY. So HX and HY need to be in the opposite direction of what they were on my other diagram. D, we got another 2-force member. So we draw that as an FAD, and that's along the 60-degree angle. So in this case, we're going to use all of our results from the previous diagram for these 3. I would probably sum moments about point C. And what I'm looking at doing is probably breaking each of these forces that are not in the X and Y direction up into X and Y components. And then I have to do a little bit of math because my distances are all given parallel to this 10-degree axis. So I'll need to take each of these distances and break them up into horizontal and vertical distances using sine and cosine of 10 degrees. And then I'll take, the vertical component of this force times a horizontal distance. Horizontal force component times a vertical distance is how you figure out your moment. All right, let's talk for just a bit about this frame that I made up. So again, I would probably, for a frame, start with a whole free body diagram. It's not always helpful, but sometimes it is. So the whole free body diagram, I guess I should put some loads on here. Pretend like there's a force right there. And I don't know, maybe distributed load on this side. So on my whole free body diagram, I need that force, and I would need my distributed load, which I like to replace with a point load by finding the area under the curve. And so then that point load would act right in the centroid of that rectangle, and it would replace the distributed load. Then at the left, let's call that point A, B, C, D, E, and F. So at A, I have a pin. So I'd end up with an AX and an AY. And at F, I have a clamp, fixed support. So I would end up with an FY, FX, and a moment at point F. So this is a diagram with 5 unknowns. So it is very unlikely that I'll be able to solve for very many of them with this diagram alone. Why don't we look at member ABC? Okay, member ABC looks like this. We have our AY and AX, just like in our overall diagram. At B, we're connected to a 2-force member. So I'm going to have the force in member BE right there. At CD, we're also connected to a 2-force member. So I'll have the force in member CD. And then I also have an external force right there. I don't know, make it 100 pounds. And there's my diagram. I have only 4 unknowns, so this is already looking like a better diagram. May not be able to solve for anything, but I can write additional equations here. I could also draw a diagram of member DEF. And these are kind of the only 3 diagrams that are going to be very helpful for this problem. This diagram ends up with FBE going down to the left, FCD going off into the left. It'll have my overall pink force, make it pink again, from my distributed load. And then it will have my same 3 FX, FY, and the moment about F on it. And that's as good as we can do with this. Every one of these diagrams has more than 3 unknowns. So that means to solve this problem, you would need to do simultaneous solution of more than one equation and more than one unknown. So my tips and hints for this part are, first of all, a whole free body diagram, definitely for trusses, and usually they're helpful for frames. When breaking up free body diagrams, follow my rules. Follow rule number 1 and rule number 2 for consistency in your force directions. Third would be, when solving, start with a diagram that has as few unknowns as possible. Start with a free body diagram with the fewest unknowns. Fourth would be, usually you want to sum moments first. Sum moments about a point with multiple unknowns. Like this one I just showed you, a great place to sum moments is point A, because it's got 2 unknowns. So that concludes this part of your final exam review.